All right, let's work through sample problem number 2. We'll start with part A. Calculate the pH of a 0.30 molar acetic acid solution, CH3COOH. So we can write a reaction that says CH3COOH. And of course, in water, we get H plus or H3O plus and CH3COO minus. And let's do our ice table. So the initial concentration of the acetic acid, 0.30 molar, and we have no products. And our change here, minus X plus X plus X. We have 1-to-1-to-1 stoichiometry, so 0.3 minus X, X, and X at equilibrium. Okay. So again, let's assume that this change is very small so that we can ignore this minus X. Okay. And let's keep in mind our Ka expression. Concentration of H plus, concentration of acetate over concentration of the acetic acid. Okay. So if we substitute that into our equilibrium, we substitute X in for H3O plus, X in for acetate ion, and the initial concentration due to the small change for the acetic acid. And we do some algebra to solve for X, and we get 2.32. Sorry about that. We get 2.32 times 10 to the minus 3 molar. And of course the negative log of that concentration, since X is our hydronium ion concentration, gives me a pH of 2.63. All right, let's work through part B of sample problem 2. Just as a reminder now, we're finding the pH of a solution that has not only acetic acid, but also a concentration of sodium acetate. So we're going to start with this same equation, CH3COOH, H plus or H3O plus, and acetate. And our ice table. So initially we have 0.30 molar acetic acid, and then we have some sodium acetate that's going to dissolve completely and give us an initial concentration of acetate equal to 0.1 molar. And given the stoichiometry here, this will decrease by X, increase by X, increase by X. So at equilibrium, we have 0.3 minus X, X, and 0.1 plus X. Now again, let's assume this change is very small. This X is very small, so we can ignore it. And let's substitute our unknowns and our knowns into our equilibrium expression. So Ka, 1.8 times 10 to the minus 5, is equal to the hydrogen ion concentration, or this is also X, times the concentration of acetate, which is the 0.1, divided by the concentration of acetic acid, 0.3. Okay. We solve for X, or H3O plus concentration. We get 5.4 times 10 to the minus 5th. And the minus log of that gives us a pH of 4.27. All right, let's consider what happened with these two different solutions in sample problem 2. When we just had acetic acid in the solution, we have a lower pH, 2.63. When we have a common ion in the solution, the acetate ion, the hydronium ion concentration decreased and the pH increased. How do these results support Le Chatelier's principle? Well, by increasing or adding this common ion, acetate, we shift the equilibrium to the left, decreasing the concentration of both products. So the concentration of this H3O plus decreases. The lower the H3O plus concentration, the higher the pH. So that's why we see the resulting increase in the pH.